Hey everyone, Mr. Smith here, and in this lesson we are going to talk about electric fields and electric field strength. So let's get started. So to start off, what is an electric field? So an electric field, and you guys have this start off in your note if you're following along with the lesson sheet, it's a region of space in which a charge will experience a force if placed inside it. So it's a lot like gravity. We know if you have some mass, it sets up a gravitational field around it. And if you put another mass in that field, it's going to, in the case of gravity, attract it. Now, in the case of an electric field, it's similar. So if we have some charged object, and the charge on that object we'll say is Q, and we place another charged object inside or close to it, it's going to experience a force. Now, gravity is always attractive. So when we put a mass into a gravitational field, and you don't need to copy this in here because I'm going to erase it in a second. But when we put a mass in a gravitational field, the field lines look like this because they are always attractive. Right? So we knew how to draw the field lines for a gravitational field. That was easy. But how do we draw the field lines for an electric field? Because it totally depends on the signs of the charge, right? If you have two unlike charges, then yeah, it'll be like gravity where you're attracting that small charge. But if they're like charges, they're going to repel and the arrows would be going outwards. So how can we resolve this conflict? So in these diagrams, we always assume that test charge QT is positive. And so the field lines are always going to be, we're always going to assume it's for what would happen if a positive test charge comes in. So again, don't copy this down because there are diagrams I believe you have on the back of your first page of this note that show this. But let's say that we had a positive charge setting up some electric field around it. Well, a positive test charge would be repelled. Excuse me. And so the field lines for a situation like this would be away from the charge setting up the field. Can I just do Control-Z? No. I had a brief moment of inspiration. It's like, oh, I can just Control-Z these guys away, but no, I gotta erase. But if the charge setting up the field was negative, well, then a positive test charge would be attracted, and the field lines would all be pointing inwards. So that's how we resolve that conflict. When we're drawing field diagrams, we always assume the field lines point in the direction that a positive test charge would move. So we now know what electric field is. Hopefully you guys have got this visual down in your notes. And now let's compare gravitational fields and electric fields. So you may want to pause the video lesson at some point to maybe make sure you have get this all down and digest it. Maybe you want to just watch for now and then pause it and get it copied down. But electric fields and gravitational fields are analogous. They have a ton of similarities. So with gravitational fields, we have some big mass M setting up a gravitational field. We bring some mass M close to it, R meters apart, center to center separation. The gravitational force is Gmm over R squared. And then if we divide by little m, we get what we call the gravitational field strength. We've already derived this. Gravitational field strength was Gm over R squared. G, Newton's constant of gravitation. M, the mass setting up the field. R, how far you are away from that mass setting up the gravitational field. And this equation we use gave us the field strength. And we know that G is a vector. This equation gave us a strength. The direction is easy. In the case of our diagram there, oops, go backwards. In the case of our diagram here, The direction of G is easy. At this point in space, the direction of G towards the center of the mass of the field. In this point in space, towards the center. So we understand that G, gravitational field strength, is a vector. That equation gave us the magnitude. Exact same parallels for a charge setting up an electric field. So you have a charge Q, big Q, setting up an electric field. You have some positive test charge, QT, R units away. The electric force, we now know, is K, Q, QT over R squared. And if we divide by that little test charge, just like we divided by the mass, this gives us the electric field strength or intensity. And its equation is very similar. K, Q over R squared, where Q is the charge setting up the field. In its direction, we can tell if it's a positive charge, positive big Q setting up the field. We know the direction is always out because a positive test charge wants to go away from it. And if the big Q is negative, then we know the electric field is always, or the electric field strength is always going towards. It just depends on whether Q is positive or negative. But we always assume a positive charge on the test charge. All right, and again, we understand this is a vector. This formula, KQ over R squared, will give us the magnitude. So if you need to pause and just make sure you get that down, hopefully you're convinced of the similarities. But we now have an equation for electric field strength. Now I'd like to actually modify what I have up here. We're going to use just epsilon. This is the Greek letter epsilon, and epsilon, we're representing the magnitude of the electric field. So when we're doing electric field strength, it's often just the magnitude. And Q, I want to stress, is the magnitude of the charge creating the field. So it's a lot like electric force, Coulomb's law. We're going to be plugging in the magnitude of the charge setting up the field. And something to notice here, so think of our equation for gravitational field strength. G big M over R squared. It depends on the mass setting up the field. The gravitational field strength around Earth depends on the mass of the Earth. The gravitational field strength around a charge depends on the magnitude of that charge. It doesn't matter, it doesn't depend on what kind of charge you're putting in the field. Just like the Earth's gravitational field doesn't depend on my mass or your mass. It just depends on the mass of the Earth. So that's a bit to copy down into your notes. So if you need to pause, just please go ahead and do that. And just in practice, we've been using 9 times 10 to the 9 for Coulomb's constant. All right. Another equation we can use as a result of this is it's an equation relating the force and the field. I'm going to keep my image right here there. So our definition for the field strength was taking that electric force and dividing by the sign of the test charge. If we rearrange that, we get electric force is equal to QT, the sign of the size of the positive test charge, times the electric field. And so we see electric force and field strength are vectors in the same direction. And this isn't anything new. So if I can go back, if we think about gravitational field, if we have some mass up here where I'm drawing, we know that the gravitational field strength will be going down, attractive, the same direction as the force, right? So again, this is not anything new. The field strength and the force point in the same direction. And just going to double check if I have anything. I do have one thing I want to add to that. A comparison here for gravity is this. And if I were you, I might even jot this down. So how long have we been using Fg equals mg? Well, now we know that G, gravitational field strength, is a vector, but how long have we been using Fg equals mg? Well, the same relationship is true for charge. Electric force is the charge in the field times the electric field strength, just like gravitational force is the mass in the field times the gravitational field strength. So these two equations are kind of analogous to each other. You may have seen diagrams like these before. These are field line diagrams, and I told you not to copy down certain things because we had better diagrams coming. So again, when we're thinking of the electric field strength, its direction is always determined by thinking what direction would a positive test charge move when let free. So if we have a positive charge setting up an electric field, a positive charge anywhere is going to be repelled, right? And that's why in the case of a positive point charge, the electric field lines are pointing outwards. And remember that the more tightly clustered the field lines are, the stronger the field strength, right? And we know that from Coulomb's law, the farther away you get, the lower the electric force. So this diagram makes perfect sense. The diagram for a charge setting up a field that's a negative charge looks similar, except all the field lines are pointing in. Again, because we draw the field lines according to where a positive test charge would move when let free. And a positive test charge would be attracted. So this middle one is a lot like gravity. Now, we can also talk about the field lines for multiple bodies. And this is an electric dipole. And if we think about this case, and I won't ask you to draw complex ones like this, but if we think, well, where would a positive test charge move? Well, if it's in the middle of these two guys, a positive charge would move away from this guy and towards a negative charge, so to the right. And then as we get maybe a little bit above, we still want to go away from the positive charge, so away and up, but then and to the right, but then the negative charge will pull us right and attract us back down again. So you get this kind of looping effect. And this is the field lines for an electric dipole. Maybe you saw those in your grade 11 course. I have a note on this in a second. But you may want to add this to your graph. How can we determine the field strength in cases like these? Because we know how to find the field strength for situations like the first two. The field strength would be K times Q over R squared. And it wouldn't matter whether the charge was positive or negative. We plug in the magnitude Q and the direction we get from thinking where would a positive test charge go. How do you find the field strength for situations like this? Because what do you use for Q? What do you use for R? Because there's two objects now. What you do is you kind of add field strengths together. So for say like a point up here where I'm drawing in green, the field strength from the positive charge would be something like this, right? Up this way, because a positive test charge would be repelled. And the field strength from the negative charge would be like down like this, right? Because it would be attracted. And then to get the net electric field strength, we add them together. I'll just say E total. And you can see because of the symmetry here, it actually makes sense that the field line is horizontal at this point due to the symmetry. So we can add field strengths together in the cases of multiple objects. And that's what I have for you there. And actually, I think my intention was to make those little markings on this slide, but those markings from the previous slide, you can just, we've got them, you can add them on there. We're good to go. So yeah, to determine field strength for multiple charges, we just add the field strength vectors together. And we'll do an example of that coming up soon. So let's actually do some examples. So what is the electric field 0.6 meters away from a small sphere with a positive charge of 1.2 times 10 to the minus 8 coulombs? Well, what I would suggest here is let's actually draw this out. So we have a charge Q, and in this case, it's a positive charge, and we're told that Q equals 1.2 times 10 to the minus 8 coulombs. So notice Q is positive here. We would have the same Q if this question said a negative charge, because it's Q here is the magnitude of the charge, right? But in this case, we actually know, like, so what is the electric field? The electric field for a positive charge is always going to be pointing away, right? So you can draw the whole diagram all the way around if you want. But yeah, always pointing away. So when we answer our question, what's the electric field? We'll get our magnitude. And then for our direction, we will always just say, in this particular problem, we can say it'll be away from the charge because it's a positive charge setting up the field. So let's do it. So what's the electric field? Epsilon equals K Q over R squared. R squared equals 9 times 10 to the 9. Charge setting up the field, 1.2 times 10 to the minus 8. All divided by, where am I looking? 0.6 squared. There we go. All right, let's bang this out. 1.2, 8, 300. Now, you guys copied this down earlier, but I think I kind of glossed over it. So we know that remember the units for gravitational field strength. This is just, and feel free not to copy this down. But remember the units for gravitational field strength were newtons per kilogram, right? The units for electric field strength are newtons per coulomb. So what this means, if I were to place a 1 coulomb charge in this field at that particular point, it would experience a force of 300 newtons. Now I might write that down. A 1 coulomb test charge would experience a 300 Newton force. So that's kind of the interpretation of that electric field strength. And we can say that the electric field vector is 300 newtons per coulomb, and it's away from Q, away from the charge. So if you're asked for the electric field, magnitude and direction, get the magnitude using our equation, get the direction by thinking about the context. If we have a positive test charge, a positive charge setting up the field, a positive guy in the field is going to want to go away. Okay, if you recall, we talked about how can we find the net field strength for multiple charges. So here we're going to do that. So we have a positive charge Q1, and we have a negative charge Q2. And we want to calculate what's the magnetic or what's the electric field going to be at point P. So right away, you guys should be able to figure out the direction. If you want to think about that for a second, pause the video and pause when you're ready. But think, where at point P, if you placed a positive charge at point P, where would it go? Well, it would be repelled from the positive charge and attracted to the negative charge. So it'd be to the right. So we already know the direction for our net field strength. It's going to be right. But let's actually get to work here. So I'm going to call, let's find the, I might actually even draw this too. This might be a good idea. So I'm going to draw a vector here representing the electric field due to charge 1. And we also know that our electric field for charge 2 will be to the right, attracting a positive charge. And so we're going to be adding those two together. But let's find those magnitudes. So E1 KQ over R1 squared 9 times 10 to the 9. Q1, I should actually maybe write capital Q with a little 1 here, because it's the charge we're using. Our Q will be different for each phase of this problem. But yeah, we're looking at Q1 right now. So that's 3.2 times 10 to the minus 9. And the question says it is 15 centimeters from the positive charge. So 15 centimeters, 0.15, don't forget to square. 9x9 times 3.2 x negative 9 divided by 0.15 squared. So 1,280 newtons per coulomb. And we can say that the electric field vector is 1280 newtons per coulomb. And we know it's to the right because we've looked at our diagram, we've thought about signs, we know it's right. And we'll just do the same thing with E2. So K Q2 over R2 squared. 9 times 10 to the 9. Charge setting up the field. 6.4 times 10 to the minus 9. Remember, magnitude, right? So we're plugging in positive 6.4. And the distance, well, it would be 27 centimeters left over, right? Yeah, because it's 42 centimeters between the two charges. 9x9, 6.4 power of negative 9, about 27 squared. All right, I got about 790 newtons per coulomb. And so the electric field vector, 790 newtons per coulomb. And again, it's to the right. We know the direction because we've kind of thought about the problem. And so now we can say that maybe E net or E total, whatever you want to do, is 1280 to the right plus 790 to the right. Add those two together. 2070 newtons per coulomb, again to the right. So when you have multiple charges, find the field strength for each individual one and add the vectors up. In this case, the vectors were along the same line, so it's easy to add them up. If the field strength vectors are, say, at angles to each other, then you can use the component method or trigonometry or whatever you feel comfortable with. The last thing we're going to talk about in this lesson is the electric field between two parallel plates. So in the case of two parallel plates, do I have this typed out? No, I don't. No, I actually have something in mind to write in here, but we're gonna have a little team talk first. So consider two parallel plates pretty close together, just some small distance apart, and they have evenly distributed charges. So one plate is negative, one plate is positive, but you have the same charge. So that's kind of in this diagram, that's illustrated by the fact that these negatives are kind of equally spaced apart, these positives are. So the same charge, same distribution. Think about if you placed a positive test charge between those plates. So what happens is, at this point, you've got lots of contributions. So this guy down here is, exerting a force up on that point charge. This guy over here is exerting a point up and left. This guy over here is exerting a point up and right. But because of the symmetry, what you're going to get is you're going to get this net force that is straight up, which is pretty cool. And actually, all the way through that plate, there's going to be one same constant force or same electric field. The field lines are going to be always from the positive plate to the negative plate, because we know a positive test charge would go away from the positive towards the negative. But the field strength is uniform. Guys, remember that the more tightly clustered the field lines, the stronger the field. Well, in this case, because of the symmetry all the way within the parallel plates, that the electric field is constant. So this means the electric field vector is the same magnitude and direction everywhere between the plates. So that's pretty cool. This kind of thing is not possible with masses because both, if you had, well, two plates, they both be attracting a mass in between, right? But with electric forces, it's possible to have this interesting idea that the force in the electric field is positive anywhere between these two plates. And it doesn't matter how close you are to the negative plate or the positive plate. It's really cool. Everywhere in this region, everywhere, the electric field strength is uniform, it's consistent, it's the same magnitude and direction. So just a little aside, well, what happens at the edge though? Because at the edge, you no longer have this symmetry. So at the edge, what you kind of get is that the positive plate pushes it out a little bit, and the electric plate and the negative plate brings it back. And then you get kind of more extreme like that, but they're always going from positive to negative. So these are called the edge effects, but most of the time are parallel plates. And I think I may have mentioned, and maybe you've heard this word before, another word for parallel plates set up like this with equal but opposite charges are capacitors. But because usually our capacitors are so close together, these edge effects are negligible. We kind of just ignore them. All right, so key ideas. Since the electric field is the same everywhere between the two plates, the force will be constant, and so will the acceleration. So we've already established the electric field the same. That means that if you place a test charge anywhere inside there, it'll experience the same force and the same acceleration, which is interesting because if it's the same acceleration, well, we know how to quantify that, and we can actually predict the motion of a charged particle inside parallel plates. Because if it's constant acceleration, we know how to handle that. Some other notes that I've talked about, for the most part but you might want to get down. So the electric field in the region outside the plates is 0, and we've talked about the edge effects. But so going back to the diagram here, if you think about what the field strength is, say outside the parallel plate, well, you would have the negative plate pulling it down, pulling a positive test charge down, and the positive plate repelling it. And if you can imagine those two plates are really, really close together, then the electric force from each plate is going to be kind of similar, because if those two guys are so close together, the difference in R is kind of negligible. And so the electric field is basically 0. Not perfectly 0, but for theoretical purposes, it's very close to 0 anywhere outside the plate, except at the edges here, we have these edge effects that we talked about. Electric field is constant everywhere in the space between the parallel plates. We got that. Straight, equally spaced, perpendicular to the parallel plates, just like we've drawn here. So they are equally spaced apart because the field is uniform. They all go from positive to negative, and they are perpendicular. So inside the parallel plates, the capacitor, a charge is not going to go, charge at rest is going to go from positive plate to negative in a straight line perpendicular. The magnitude of the electric field depends only on the magnitude of the charge on each plate, which means I don't have a figure 12, so you can just refer to our diagram. But this is something important too. The electric field strength inside parallel plates is dependent on the charge per unit area on each plate. So the electric field strength only depends on the charge. That's it. It doesn't matter on how far apart the plates are, which is pretty interesting. So if you have two parallel plates with and a charge on each one, and you have a certain electric field strength, if you put those plates closer together or farther apart, the math says that the electric field strength is not going to change. It only changes when you increase the charge in each plate. So a really quick example, and it's actually not even like a lot of math here to do, just to reinforce that. So we have the magnitude of the electric field between two parallel plates is 3.2 times 10 to the 2 newtons per coulomb. I guess that's just 320. For part A, how would the field differ if the charge on each plate were to double? Well, a big idea with parallel plates, capacitors, is this. Remember, electric field strength is proportional to Q. And what does that mean? It means if you double Q, you double the field strength epsilon. If you double Q, you double epsilon. So I'll just say E nu would be 640 newtons per coulomb. You just double it. For part B, though, remember, field strength is proportional to Q, not distance. So in the case, if you were to separate those two parallel plates or push them closer together, the new electric field strength is just the same, 320 newtons per coulomb. So before we finish off and just talk about some applications, there's something to be aware of. So when we were talking gravitational field strength, we only had our one situation. We had gravitational field strength is Gm over r squared. In the case of electric field strength, there's going to be two cases now. There's going to be problems where we have point charges setting up an electric field, and those problems can be handled the way we handled these two examples here. But then we'll have situations where we have parallel plates. And in that case, the electric field strength is not kq over r squared. It's just the same value everywhere between the two plates. And in those cases, we're going to calculate the electric field strength by using this formula. And we're not going to quite get to that this lesson. I actually think it's for a topic for our next day. But yeah, you have to keep in mind when we're talking electric field strength, we have two cases. When we have point charges setting up a field, we have different field strength depending on how far away or where you are. And we have parallel plate where the field strength is constant. A couple applications, interesting applications of capacitors. So one is precipitators, so electrostatic precipitators. So the long and short of it is you've got this, what we say, flue gas. That's basically like, if you've seen the crap like coming out of smokestacks, that's it. Dust, smoke, pollution particles. If you send that flue gas through a series of capacitors where we have positive plates and we have wires with a negative charge, and this isn't need to know, this is just for interest's sake. If the charge on the wires is actually really, really big, so lots of current flowing through a big negative charge, what happens to the air around it is it becomes ionized, meaning all the electrons in the air are actually allowed to kind of free themselves from the air particles. And those electrons get attracted to the plates. And then you get all this flue gas and you send it through these plates, and the electrons, for lack of a better word, just really loosely speaking, they stick to these flue gas pollution particles. And because they have a negative charge, they kind of stick onto the parallel plates. And when you vibrate these parallel plates, that ash, that pollution that's collected, can be stored and disposed of, and it doesn't exactly go into the air. So a simplified explanation of how precipitators work. Another example of electric fields in nature is hammerhead sharks. So hammerhead sharks, they're the reason they have, well, obviously they're called hammerhead sharks because it looks like they have a hammer on their head. But the purpose of that is actually for them to create an unbalanced electric field, and so that they can detect prey. Because if we think about how our muscles work, it's all from firing little electrodes, right? And electric signals from our brain to our muscles, etc. And because of the hammerhead shark's design, it can actually detect those weak electric fields. And so it can detect fields with a strength of about 6 newtons per coulomb. And so that's why it can kind of hunt for those goby that hide beneath the sand in the ocean floor, is because if it's close enough, it can actually detect the electric field given off by that fish. So that's pretty cool. All right, so what's next? We've talked about electric field strength. We've compared it to gravitational field strength, and we saw there were a ton of similarities. But we have that one extra case with electric fields where we have parallel plates, and it's constant everywhere between parallel plates. What we're going to do next is we're actually going to make use of a parallel plate, a specific application. Inkjet printers actually use parallel plate capacitors to deflect and control where ink droplets go on a piece of paper. So we're actually going to learn how inkjet printers work and do some problems related to that. So it should be fun. It won't be a crazy long lesson. It's more of just a specific application. But for now, you guys have some practice on electric fields. I think we'll stop there for now. Hope you guys are staying well. Have a great day, and we'll see you soon.